is Martina Lanini, who will be telling us about Torus actions on cyclic quiver-Grassmannians.
Thank you very much. And so thank you very much for the invitation. It's a pleasure to participate in this meeting. I really enjoyed yesterday's talks. So let's see what we can do today. So what I'm going to talk about today is joint work with Alexander Puetz, which is a postdoc here in Roma Vergata. And so let me start. So I spent some time just telling you why one should care about torus actions on varieties. So probably you're already convinced it's interesting. If you're not, I hope I'm going to convince you. And then, so I spent some time on it. Then I'll recall something about quiver-Grassmannians, and then I'll construct these actions for you. So it's somehow a first step of a bigger program, and I hope you'll, I don't know, you'll get excited about it. I think there are a lot of like possibilities one can, a lot of directions one can take. So okay, so let me start with so nice. You read? Yeah. Okay. Torus actions. Well, maybe it doesn't work really like this. Better. Okay. On algebraic varieties. So okay, the very starting point is just X, which is a complex. Well, I'll focus on projective algebraic variety. Okay, and so a standard example we might have in mind is just the variety of complete flags. So FLN+1. So inside CN+1. And now I want some algebraic torus to act on it. So that's an algebraic torus action. So in this case, what I have in mind is the action of diagonal invertible matrices. Okay. So this is GLN+1. So here we have complete flags inside CN+1. So I can fix some standard basis, and then the torus is just rescaling it. Okay, the standard basis vectors. Or in general, I just have GLN+1. It naturally acts on CN+1, and this action preserves all inclusions, and so in particular, complete flags. Anyway, we have this torus action. And that's a nice torus action in this sense. Okay. So why do we want to look for something like this? Well, because what happens is that, so if the action is nice, and I'll specify what I mean by this in a few minutes, then the local behavior of such an action, well, in fact, gives us information about global properties of the varieties. So let me say just global information about X. So what do I mean by global information? Well, for example, if let's say T is really small, so I have just a C star action. Well, if the C star acts with a finite number of fixed points, well, then this number of fixed points gives us the Euler characteristic of the variety. If, well, again, so it also gives, if it is, let's say, for example, just to make sure nothing is going wrong, if we have a smooth variety, it also, the sister action also gives us a cellular structure, and by counting cells, I get the Poincare polynomial. And today we actually we are interested in a bigger torus action. And if I have a bigger torus acting in a nice way, then I can even get information about the ring structure of the cohomology. Okay. So let me say cohomology ring, for example. Well, in particular, I get information about the equivariant cohomology, but if the action is nice, I can just recover the usual cohomology of the variety. Okay. So what I'm going to recall for you now, it's a result of Goretzky matrix person, so which is a version of the localization theorem. But in fact, this is what's known nowadays as GKN theory from their names, but it's the end point of a longer history. So it started in the 60s already with the work of Attia, Bott, Segal, Verne, and then even the result I'm going to state is actually, it appeared already in the 70s in a work of Chang Skjelbred. But anyway, so the theory is nowadays known with the name of GKM. So let me use this terminology. So definition, again, I'm focused today on complex projective algebraic variety X, so equipped with a torus action. The torus is T action. So it's called GKM variety, or maybe the pair is a GKM pair. And again, GKM comes from wherewe, Macpherson. So if, well, first of all, I have a finite number of fixed points. I have a finite number of one-dimensional orbits. So let me tell you right away that this is a very strong, it's sort of a strong assumption. You can get rid of it and still the theory can go through, but we assume that for today. And then I want the odd cohomology groups with rational coefficient to vanish, as well as I is even. All right, so that's what for me today a GKM variety is. So somehow you might have heard of it, and maybe usually you've heard something like equivariantly formal space, but under the assumption of finitely many fixed points or one-dimensional orbits, it's enough then to assume that the cohomology groups with rational coefficients vanish in odd degrees. So if you have something like this, so if you have a GKM variety effect, so GKM is for us again projective. Usually you don't have really to assume that, but it's what is the class of varieties we're interested in today. So if we take a pair XT as before, so we can say something about the one-dimensional orbits. So, so if O is a one-dimensional orbit, so what happens is that, so one-dimensional orbit for the torus means it's a C star, right? And so now I can close it up. And what happens is that it's smooth. So this is isomorphic to a P1, so which is obtained by adding two fixed points to this C star. And so what the torus does is just it rotates this P1. Okay, so I read it up. So the closure of O is nothing but my one-dimensional orbit union two fixed points, okay, distinct fixed points. So it moves for X and Y in XT. And again, as I was saying, there's nothing but, oh, I still have a little bit of space. So it's a P1. So I have X, Y, and now the torus here acts rotating the sphere. So now, well, it is a P1. I can write down two isomorphisms with C and infinity, okay? So, well, I can write even more probably, but let's say, so I have my two fixed points, and once I can have X playing the role of infinity, and once I can have Y. So the point is that the torus, so this is a C, so it's a one-dimensional vector space, okay? That's a one-dimensional representation of the torus. So the torus has to act on it by a character. So that's a one-dimensional T-rep. Okay. So meaning that the torus acts by a character. Okay, so some alpha in the character lattice. Okay, so these are homomorphisms of algebraic groups from T to C star. So, and it's an easy exercise to see that. So if I take the other atlas, then T is going to act via minus alpha. Okay, so this character is uniquely determined up to a sign. So in what I'm going to say next, I'm just going to talk about the character by which the torus acts. That's some ambiguity, but it doesn't play any role in what's going to happen afterwards. Okay, so we have some sign, but it's not playing any role. So far, we have our variety with a T action, which is nice in the sense that for me it's a GKM variety. Meaning that, once again, I have a finite number of fixed points, finite number of one-dimensional orbits, and only cohomology, only in even degrees. All right, so now let's take our pair, GKM. And now what I can do with that is a graph. So I think some of you have heard me already talking about moment graphs. So that has been somehow my favorite object for several years. So I can produce a graph, which is called the moment graph. So that's a graph which is nothing but the one skeleton of this action. Okay, so I have as vertices the fixed point set. Now I have edges, and these are nothing but let me write closures, so one-dimensional orbits. So by what we said before, so the remark we had before, we have these P1s, right? So I have a T star, which is a one-dimensional orbit. I close it up and I get exactly 2 fixed points. So it's drawing for me a graph. And I want to color these edges, and I color them via the torus characters. Okay? So they're labeled edges by torus characters. Okay? So this label corresponds to alpha we had before. Okay, that's again uniquely determined up to a sign. So example, so it's the example we had before. So if we have the variety of complete flags inside Cn+1, and our maximal torus T1 Tn+1 inside GLn+1 as before. And if I take the standard basis of Cn+1, E1, En+1, again by letting the coordinate Ti on the diagonal of the torus rescaling EI by the appropriate complex number, then the T fixed points are nothing but coordinate flags. Okay? So meaning that these are the complete flags in Cn+1 whose subspaces are spanned by a subset of the standard basis vectors. Okay, and so by first looking at which is the first vector of my, so the first line of the flag, and then by looking at which extra standard vector I have to add for the 2-dimensional space and so on, I get a permutation. Okay, so that's the same as the symmetric group. So fixed points are n+1. Permutations over n+1 letters. And now the one-dimensional orbits are as follows. So I take 2 permutations, sigma and tau, and they're connected by an edge in this moment graph if and only if I get tau from sigma by left multiplying by a transposition, well, or right multiplying anyway. Okay, so a transposition ij. And now it's an easy exercise to check that the corresponding character is epsilon I minus epsilon j if epsilon k is the character taking the general matrix T1 Tn+1 to Tk. Okay. So it's a basis of the one generator of the character line. All right, so that's well, that's nothing new. You've probably seen that a bunch of times. That's the so-called Bruja graph, okay? Type A. All right, so what do we do with that? We said we could recover some global information. So in fact, so far we've been discussing local behavior. So we have fixed points and one-dimensional orbits. So okay, we can do that. So let's see. So first of all, I have to add some notation. So let's denote by S the equivariant cohomology of a point. So if you're not happy with equivariant cohomology, that's just a polynomial ring. So which number of variables the rank of the torus. Okay, so if you want, you take your character lattice, you extend the so you base change it. So it's not a lattice anymore, it's a Q vector space, and you take the corresponding symmetric algebra. So that's the cohomology, equivariant cohomology of the point. So now, of course, the fixed point set is included in the whole variety X. Okay. And so I have a pullback map from the cohomology of X to the cohomology of the fixed point set. Once again, also the t-equivariant cohomology is functorial. So I have a pullback map between equivariant cohomologies. Okay, these are algebras over, well, these are S modules. And now in the result I'm going to state for you, we're going to have an explicit realization of them. And so you also can, you can forget about HT if you don't like it, or you just have a combinatorial description. So here, let me just add you something. So here we have the equivariant cohomology of the fixed point set. Well, but we assume that there was a finite number of fixed points. So meaning that they're all isolated. So this is nothing but the direct sum of the equivariant cohomology of a single point, which was S. We call it this way. Okay? So one for any fixed point. And now the theorem, which is relevant to us. So again, I'll call it GKM. So it's the following one. So this pullback map, but again, it's just a version of the localization theorem. So the pullback map is an injective map. Well, more precisely, is a homomorphism of S algebras. And then the image is the following one. So we can describe this explicitly. And it is, well, so the image lies inside this direct sum of polynomial rings. So we pick a polynomial for any fixed point. And now, well, the main point was that we want to use this graph, right? So so far we used just fixed points, which were the vertex set. And now we still have edges and labels. Okay, so what these edges and labels are telling us, well, they're giving us some gluing and compatibility conditions between these polynomials. So the difference between fx and fy, so these are two fixed points, is, or maybe we can write this way. So fx is congruent, so it's the same as fy mod alpha. So if x and y are adjacent on the graph, and alpha is the character corresponding to the one-dimensional orbit. Okay, so let me try to write this. So
this alpha depends on x and y, right?
Yes. Yeah, I'm trying to, let me see if I managed to write it. So for any orbit closure, which is O union x and y, and then maybe here I can write this, and I write n alpha here. Okay, so it's the speed as before. Okay, so I have my one-dimensional orbit closure. Inside there, I saw that there was if I removed one of the fixed points, I have a t representation, and the torus is acting on this t representation via alpha or minus alpha. Doesn't really matter because I'm like considering just modulo alpha. So if it's alpha or minus alpha, I don't care. Okay? It's the same condition. But in fact, I can even do it over Z. Here I'm just I don't want to deal with that, so we're just over Q, so we have no problem. But again, even if we were over Z, we wouldn't mind to have plus or minus alpha. Okay. Now the remark is that actually, if we, oops, I want to write it black. So actually, if we really care about cohomology, we can just recover it by base change. Okay, so the homology of X, and cohomology here means with rational coefficients. It's just the equivariant cohomology, so this is isomorphic to this ring. And then I just base change it. Okay, so I kill this equivariance, I kill the Torus action. All right, so, but now why are we happy with that? Why do we like it? Okay. So why do we like this description? So that's what I mean. Okay, so that's what I want to spend next 5 minutes on. So why should one care about this definition? So, well, that's a longish remark. So I want to tell you, so I want to give you a list of reasons why this somehow this ring, so how this ring has been extremely useful in our example we had before. So for FLN plus 1. And actually, I mean, I could just talk about whatever Kac-Moody group for most of the points I'm going to list. But yeah. So, well, so why so in our example, so there was FLN plus 1, I keep with the CN plus 1 star action or CN action. So, well, first of all, the Bruja graph itself, well, has been studied from a combinatorial perspective. So it's interesting itself. Well, okay. But even more, so this, let me say, combinatorial approach also led to an interesting result. So the Bruja graph is a graph, okay, we saw it. And so what one can do is to, for example, study spatial matchings, which is a way of, if you want, arranging pairs of vertices. And by doing that, on the Bruja graph for Sn, so for, in this case, for FLN plus 1, we said, well, Brenti, Caselli, and Marietti managed to prove some special cases of a conjecture about Casa-Lucy polynomials. So that's a conjecture by Lucy and Dyer, which says that, well, we have this family of polynomials which are extremely important, and they're indexed by pairs of elements in a bar group. And so the conjecture was that I don't really care about, so they don't really depend on a specific pair, but only on the Bruja interval, so on the interval between the two elements, which index in the polynomial. So that's, somehow it's a very strong thing, because Casa-Lucy polynomials are measuring also singularity of sugar varieties, are giving information, so are Poincare polynomials for intersection cohomology. So it's sort of very optimistic as a conjecture. But somehow by studying combinatorics of the Bruja graph, Brenti, Caselli, and Marietti managed to prove that for the symmetric group and for the interval starting with E. Okay, so already the Bruja graph can do more than just being an interesting combinatorial object, even if would be already nice. Well, then this S algebra we have here, which I happily have here with all this red square. So let me write this, the S algebra, the S algebra star. Well, it's not really pretty, it's not, doesn't really have a nice description, but in fact this is isomorphic as an S algebra to the center of the principal block of, well, let me say, equivariant category O. In this case, for SLNC, well, in fact, if you were playing with whatever, let's say first, maybe just a linear algebraic group, and then a parabolic subgroup, then we will get something which is isomorphic to the center of some singular block of the category O for the corresponding finite dimensional complex Lie algebra. And even for Kac-Moody, in the Kac-Moody case, we have to exclude the critical blocks, but apart from that, you get similar description. Okay, so in terms of the homology, that's actually, well, originally work of Fiebig and zergo, first zergo in terms of what are now known as zergo bimodules, and then Phoebe gave this realization. Well, I've been also working with this sort of stuff for a while. Well, then another nice thing one can do is to give a concrete realization of Weil group actions on cohomology groups. And let me say it this way, HT mod P. So in this case would be SLN mod B. But then in general, you can take whatever algebraic group, let's say reductive, and then you quotient by some parabolic subgroup. And by looking at the underlying combinatorics of this graph, you can describe explicitly these actions. So that's a work of Juliana Timotsko. Finally, well, you have application in Schubert calculus, because you can give explicit formulas for what are called localized Schubert classes. Okay. So that's a preferred basis for the cohomology, not only for type A, but in general for generalized flag varieties. And that's a formula which is known, I think, as Billy's formula, which actually, I have to mention this, appeared already in Anders Jansa-Zerger's book in Japan. Anyway, so it's known as Billy's formula. So today, so I hope you got convinced that it's very nice to have well, not only a GKM structure and the variety, but a nice combinatorial description of the moment graph arising from it. So that's what that motivated our work. So today, we want to equip certain quiver-Grassmannian with the structure of GKM varieties. And let me also say that is important, whose moment graph has a combinatorial description. So this is important because exactly because of what I just said. That, I mean, if you just know that this is a GKM variety, you cannot control the graph. Somehow you haven't really gained much. So the main point is that you can really use, I mean, if you can control the graph, you can really apply what you got. So also let me mention that somehow we are particularly happy about our GKM structure because we recover. So in some specific cases, we get as a particular case, the case of FLN plus 1, and we recover exactly what we knew already. So we feel like that it's a very natural action. So now I think it's time to talk about quiver-Grassmannians. So in fact, I'm just going to focus on the equioriented cycle to save some notation, because it's some of the example we really deal with. So the equioriented cycle is nothing but, well, a cycle. So I start with 1, then I have an arrow, here I have 2, 3, and so on, up to n, and then I go back to 1. So it's just an oriented cycle, delta n. And so now definition, a delta n rep is a pair m given by m0 and m1. So where? So m0 is finite dimensional complex vector space equipped with Zn grading. Okay, so M0J is finite dimensional. And this is giving me the gradient. So if you have already seen a quiver reps, usually what you do is that you provide, so you give one vector space for any vertex, and then the edges are giving you maps among them. But since we are in this delta n setting, we can just express it this way. And so M1 now is an endomorphism of M0 as a C vector space, so it does not preserve the gradient. In fact, it sends so such that M1 of M0J is contained in M0J plus 1. So this is what you would say usually. You have maps between, given by the errors. Okay, so a subrep instead is just a Zn graded vector space. So a sub representation N of M of a delta N rep, okay, is Zn is a Zn graded C vector space. Okay, so meaning N again is isomorphic to some Nj. Well, such that this is compatible with a gradient on M0. So Nj is contained in M0J, and then is preserved by the endomorphism. Okay. So we want that M1 of N is contained in N. Okay. Right, so now I read here the title of this section is quiverGrassmannians, so we want to define that. And so if the usual Grassmann variety is the variety having as points subspaces of a given space of a given fixed dimension, well, we're going to do something similar. So the quiverGrassmannian is going to be a variety whose points are sub-representations of a given fixed representations whose graded pieces have a prescribed dimension. And so indeed, in the general setting, if I take delta, or delta 1 is boring. So if let's say if I take just a quiver with one vertex, then I recover just the usual Grassmannians. So let me write the definition. So I take M, delta N rep, and then I take a collection of non-negative numbers, as many as the vertices of my quiver. Okay, so that's the called dimension vector. And then I define dm. So as a set, these are the sub-representations. As I was saying before, well, the dj's are telling us what the dimension of a single graded piece has to be. So far it's a set, but it is clear that this is contained in the product of the Grassmannian dj mj0. And this, the condition on the dimension is a closed condition. Okay, so I really get a complex projective algebraic variety which is in general singular and can also fail to be normal. So, well, that's interesting because, so that's what was scaring me at the beginning a little bit, because monograph techniques have been applied mainly to normal varieties. Okay, so sugar variety, for example, they're all normal, and this is not the case in general. All right, so this is the sort of varieties we want to work with. So now I've restricted to delta n. Actually, I want to make another assumption, but still there's, so I'm gonna list for you some examples and convince you that it is still an interesting class. So from now on, M will be not only a delta n representation, but also nilpotent. Well, nilpotent means just that the operator, so the endomorphism M1 is nilpotent. So let me give an example of that. So let's pick a vertex of our delta n. So it's the same as I and Z mod n. And then L, which is a length parameter, as the letter L says. And now I start by formally defining M0. So that's an L-dimensional C vector space. And then I write something about the degree. Okay, so I impose that the degree of WK is just I plus K minus L, of course, mod n. And then my endomorphism M1, well, it has to go from M0 to M0, and I move in one degree to the next one. And what it does is it sends WK to WK plus 1 if K is different from L, and 0 if K is L. So, well, in terms of the basis, then what I'm doing, well, I can immediately see that it is nilpotent. Okay, that's just this matrix. Okay. And then if I want to visualize it, so what I can do is to take my delta n, and then I put a basis vector on top of the corresponding degree. Okay. And then I have an arrow when my operator is sending one vector to the other. So I have a sort of string, something looping around my delta n, okay? Starting in I and, well, or ending in I of length L, okay? So I'll call this guy UIL. That's for sure a nilpotent representation. And our fact is that it is not only one nilpotent representation of delta n, it is indecomposable. And then whenever I have an indecomposable nilpotent, then there exists I and L such that M is isomorphic to UIL. All indecomposable nilpotent representations are of this form. Well, on the other hand, the category of representations of a quiver is Schmidt. So whenever I take a nilpotent representation, what I get is that I can write it as a direct sum of some UIL, okay, for some multiplicity space. Well, but now I remember that for me, representations were always finite dimensional. So there's going to be a maximal length that I can reach. I call capital N. That's called nilpotent parameter. So L from 1 to N. So this AIL can also be 0. And then now I can let it vary on the vertex set of delta N. Okay, so now why do I care? Well, first of all, because if you haven't seen that, I can give you an exercise. So for example, if you take M isomorphic to U N N exactly N plus 1 times, okay? And then you look, you consider the Grassmannian with dimension vector 1 to N of M. Well, this is isomorphic to the variety of complete flex in psi Cn plus 1. So it's our FLN plus 1. Well, then that's another class of quiver-Grassmannians or of varieties which can be realized as quiver-Grassmannians for delta n, which are linear degenerations of FLN plus 1. These were introduced by Cerulli, Fang, Fagin, Fourier, and Reinecke a couple of years ago. So in fact, I'm cheating because it's enough to to even open up your delta n. In this case, it's enough to have a string with n vertices, but whatever, I recover also all of this. And then also some finite dimensional approximations of GLN of fine Grassmannian or a fine variety can be realized this way. So the fine Grassmannian is an invariety. You need some finite dimensional pieces to build it up. You're invariated. Some of these pieces, well, all of these pieces in one of the in realizations can be realized this way. Somehow this description was given by Alexander Puetz in his PhD thesis. So in terms of pure Grassmannian. All right. So that's a big class. So I would say a variety we can. So for example, there's plenty of also Schubert varieties you can realize this way of type A. Anyways, so a lot of varieties we might be interested in, and many more. So, okay, let me now take M, which is nilpotent. Okay. So M is nilpotent, and as I said, has this form, right? So I'm not gonna write anything about the indices. So L is varying from 1 to capital N, and I in Zn. So now from the way we describe UIL, we have sort of preferred basis, okay? Or maybe I should be more formal. So the underlying vector space. So UIL0 has a preferred basis, which is this W11, W1AI, WL1. And then since I have AIL copies, I get up to W1AIL, WLAIL. Anyways, it's the basis we had before, just repeated the correct number of times. And also, if I take then M0, which is, as I was saying, this is the underlying vector space. Well, this again has a basis, which consists of all these yi's, j's, b, which I can rearrange according to the degree. Okay, so these are basis vectors of degree I. So from all this, I can produce another quiver, which is called the coefficient quiver. So that's a sort of a combinatorial gadget one can always associate to a quiver representation, and it depends on the representation on a preferred basis. For us, we fix it, and whatever, I just call the coefficient quiver, QM, which has its vertices, well, the elements of this basis, and now edges, well, let's say B1 and B2 from the basis, they're connected, so arrows are oriented in this case, as for delta n, but that wasn't the case for the Bowman graph. If and only if, so my endomorphism M1 sends B1 to B2. So as I was saying before, for example, for UIL, here, we just get a length L segment, okay, that we can wrap around delta L if we want to remember the degree. Okay. So, and now, well, I remember again this Krull-Schmidt result, everything is just direct sum of this UILs. And so I realized that QM is nothing but a disjoint union of UIL segments or strings. Okay, so one for each indecomposable summand. Okay, so I have this graph, and it has a lot of connected components, one for an indecomposable summand. Now another remark is that any vertex of QM or equivalently any basis vector. So let me write in terms of vertices. Any vertex B, because it's an element of the basis, of QM is uniquely identified so it has like two numbers. I give you two numbers so you understand which vertex it is. And these two numbers are, well, one is the segment it belongs to. So two pieces of data, okay, which I denote by SB, and then the position it has on the segment. Which I denote by PB, okay? And then here one should be, that's a bit careful, just say that the position of W1 instead of 1 is called 0, but whatever. I mean, it's just a technical thing to get rid of a shift by -1 in a formula I'm gonna state, okay? Anyway, so I pick a point, this will belong to a unique segment, will have a unique position. So these two pieces of data uniquely determine the basis vector. Okay, this is now enough to define the action I want. Remember that the whole story started from, yeah.
May I ask a question?
Yeah,
so do
sure.
I understand correctly that this S of B is just some concrete indecomposable summand, right?
Yeah, exactly.
Okay.
Yeah, the idea is that if you want to, so somehow I like, so at some point I would like to just talk about the graph, but the idea is that in terms of the representation, you have your M, it decomposes uniquely as a direct sum of indecomposable, and you're just saying that a basis vector, well, it is, since all bases are ordered, it is uniquely determined by the indecomposable summand of the position in the basis. That's all.
Okay, thank you.
Yeah. Thanks. No, it's important. Any other questions? All right, so now I just wanted to remind you what we are doing. So we wanted to define a torus action. We haven't done it yet, so that's what I'm gonna do it now. So let me just call A the number of indecomposable summands, which is the same as sum in all these AIL, so all the multiplicities. So this is number of indecomposable summands, which is also the same as kinetic component of the graph, UIL segments in QM. And now I first pick, so a torus, which is A plus 1 copies of C star. Okay, 1 plus A, actually. I want a parameter, and then all the other copies of C star have a corresponding indecomposable summand. So first, I'm not going to define right away an action of the Grassmannian, but on my vector space. Okay, so that's an underlying vector space. And so, so maybe let me just say M0. Okay. So I pick a point in here. There's going to be some gamma 0, gamma S1, gamma SA. So this is just to remind you that they correspond, so these parameters correspond to segments or indecomposable summands, as Evgeny was telling us. And so I have to tell you how gamma bar underline is acting. Well, I tell you how it acts on a basis element, and then we just extend it by linearity. Okay. And so here, this is just rescaling the vector by gamma 0, which is this extra parameter, which keeps track of the position of the points on the segment, so P of B, and then gamma of the segment corresponding to B, and that's the number I want to multiply, sorry, B by. So it's just rescaling that. And now the lemma is that this, this induces an action on the quiver-Grassmannian. Well, let me just make a remark. Well, the remark is that T is not a subgroup of the automorphism group as a delta n representation of M. So if it were, of course, a subgroup of the automorphism group of M, then that would be okay, right? Then, I mean, you can just always prove that if you have an automorphism of your quiver representation, then it induces also, I mean, every element gives you an action. So you're also going to get an action on the corresponding quiver-Grassmannian. It descends to the quiver-Grassmannian. Well, this is not the case, but still it induces an action. And that's some of the interesting thing. Well, in fact, it almost induces, it is almost contained, is an automorphism group. It would be contained if we forgot about the first parameter. Okay, so this is indeed contained. But that wouldn't be good enough for us. So remember, we had this requirement about finitely many one-dimensional orbits. And if we drop the extra dimension, that extra rank, we lose the fact that you have a finite number of one-dimensional orbits, which is really central. Okay, so theorem. Well, the theorem is somehow what you expect at this point, is that, well, okay, as soon as D and G are such that the corresponding quiver-Grassmannian is non-empty, I'm not going to write it, that's just the variety you want to deal with. Well, the above T action induces a GKM variety structure on GRU-DM, and then the corresponding monograph can be combinatorially described in terms of QM. So let me comment on both points. So, well, first of all, so to show, so remember the definition of GKM, I recalled it already several times, had, well, three requirements. So finitely many fixed points and finitely many one-dimensional orbits. And that's something you can really just see. So you list them, and these are sort of combinatorial objects. And then we needed to show that the cohomology vanishes in odd degrees. And in order to do that, we produce a C star action via, well, a subtorus of T, so a co-character, if you want, a regular co-character, which gives us a, well, in fact, a BB decomposition of this variety. Okay, so usually you can do that if it is smooth, but also if you're lucky. You have a nice interaction, you also get some cellular structure on the variety, which is, I mean, which implies so that you don't have cohomology in odd degrees. So the corresponding moment graph, so I have 5 minutes. I'm wondering whether I should try to tell you something about the combinatorics. Let me maybe write something, maybe for 4 minutes. I'll see where I get, and then I have a picture, which I hope can better explain, unless there are questions, and then I don't know. Okay, so more precisely, let me say a few words about the graph. So more, oh, I've lost 1 minute already, precisely. So, well, I have to say what the edges are of the graph. So what are the fixed points? Well, I told you I have some combinatorial gadgets. So these are what are called successor closed subquivers of the coefficient quiver QM of dimension vector D. Okay, these are successor closed subquivers of dimension vector D. So now successor closed just means that we have sub-quivers, so subgraphs, okay, which have the property that whenever you have a vertex, so I write Q prime 0 is the vertex set, and whenever you have an edge in the coefficient quiver, QM1, the set of edges, well, then you also need to have the other vertex, okay? So if you have the source of an arrow, and this source is in the subquiver, you also have the target, okay? Then also W is in Q0 prime. So that's what means successor closed. And then dimension vector D just means that, remember that somehow from the coefficient quiver, so the vertices of the coefficient quiver were really basis vectors for the underlying vector space, M0. And so in particular, you can look at the span, so the subspace generated by the vertices containing Q prime, and you want that they have the prescribed dimension once again. Okay. So what you're saying is that the dimension of the span over C of Q prime 0, the vertex set, intersected with the vectors of degree J in the basis is dj. Okay. And then the edges, okay, 1 minute. The edges can be read off so in this way. So you have an edge from Q prime to Q second. If and only if somehow there's a procedure, so you get Q second. So Q second is obtained from Q prime by, so maybe I can say it in words. So your QM was a collection of all these UIL segments. And so a subquiver is going to be just, well, uniquely, it's always full, so it's uniquely identified whenever you specify which vertices you are taking, because they're all successor closed and so on. And now what you want to do to have an edge is to cut an initial piece of a segment and to glue in to another segment in such a way that you're still a subquiver of QM. So that's somehow that's what's happening. So by cutting and paste an initial, let me just say obtaining from Q prime by cutting an initial part and paste an initial part of a segment. And the labels can be described in terms of the gluing vertex, okay, of this moved part. So it's, my time is over, so let me just show you a picture, which is this. Oh. That's, Yevgeny knows this, because this also appears it's this, the generate flag variety. So it's not even a delta n rep, it's just because I was so lazy. But that's, this is somehow also a sugar variety in a type A flag variety, partial flag variety. So it's, in fact, in this case, it's a variety which was already known, but I wanted to make sure I wouldn't mess it up. So let me just notice that, so what I was saying now about gluing and pasting. So for example, yeah, here, this edge, what you're doing is that you pick this segment, you cut this initial part, and you glue it here. Okay? And then this edge disappears because you don't have this anymore. Or in here you do the same. You cut this, you glue it here. But you can also move completely down a whole segment because it's still an initial part. Anyway, there is a combinatorial description of the moves you can do, and you can read off the labels from here. So, and that's all I wanted to tell you. Thank you very much.
Thank you. Are there any questions for Martina?
I have a question. Well, I have a question too. Okay.
Okay, but maybe we can start with Yevgeny and then go to Erhard.
So my question is as follows. So your quiverGrassmannians are labeled by these numbers A, I, L, and the dimension vector D, right? So do you have some description of this data for which the quiverGrassmannians are, say, smooth or irreducible?
I mean, that's something I really like to, because at least, now we have some conjectures though. No, I mean, yes, we do have some conjectures. So irreducible, I guess this you can control it, right? Because it's you look for, yeah, I think this is something you can do because you look at the number of irreducible sub-representations, right? I mean, the isotypic component. I think I've lost you all, or I've lost only Yevgeny? Oh no, I've lost Yevgeny. Okay. Maybe here you are.
I can hear you.
Yeah, can you hear me now?
Yeah, I can hear you.
Okay, good. Now, what I was saying is that I think as for the irreducibility, I think it's something. Probably you have also your paper with Giovanni and Marcus. So you look for the number of sub-representations of a given type after isomorphism, and each of them gives you an irreducible component, right? I would say. So you fix the dimension vector, right? And then you have to look, yeah, I think that's for irreducibility, but we don't have like a combinatorial criterion yet. And for the smoothness, I think now, so I mean, you can, so what I'd love to see is that someone, now we have a nice graph, right? And for, let me say, so sugar varieties, if you look at the Brugge graph, you can control where you have singularity just by looking at the tangent space. You have this pattern avoidance criterion. And so my hope is that playing with the combinatorics of the graph, you can get something similar in this generality. But I haven't played with that yet. Yeah. So not yet.
Thank you.
Right.
So I think, was it Erhard who had a question also?
Let's start with Hugh.
Oh, okay. Okay, Hugh.
Right, thank you. And thank you for the very nice talk. I was curious if you could. I mean, the things you said seemed like they would have applied if instead of having this cyclically oriented quiver, you had maybe even any, gentle algebra. How much of that, like how much can you relax the assumption that your quiver was a
so no, I think we can. So now we are trying with Alex to generalize that. So we're still thinking in terms of quivers, and so far we got. So what we can do is so we can consider whatever tree we have. So if you have a tree as long as you want, so it's a lot of like AN, but like oriented in such a way that you have a tree. It's good. Then you can also glue a delta n at the end. So we can do now actually. So for special string representations, somehow if you look at what we need, they're really, so it's not that much. It's not really so much about delta n. It's just because delta n has such a nice coefficient quiver. And then you can play the other way around, right? So to see what were the nice features of QM in this case. And that's what you can ask for. But in fact, so what I didn't mention is that a nice thing we could do somehow is to prove that you can produce a nice basis, like the Schubert basis for the cohomology of these varieties. And for this, you need way less than a C star. So I mean, way less than a cellular structure, which is some of what we are always looking for at the moment. or you can relax even that. So I don't know. I'm pretty optimistic, but I don't know yet how far we can push. Yeah.
Okay, thanks.
Thanks.
So are there other questions?
May I ask one more?
First, if there's anyone else, and if not, we'll return. Okay.
Well, my question was the following. So I was just wondering about the C here in your theory. So I assume that this is an abbreviation for any algebraically closed field of characteristics 0.
Oh, now even more. So I know,
So
I
that's
mean,
an
probably
abbreviation
Kirill
for-
is not there, right? Because you would
No.
complain very much about my talk.
Is
Yes.
it an abbreviation for any field of characteristics 0?
But where is the, no, I mean, here I was just taking Q, I guess, right? It was, no, it was a bold, so must be BQ. But just because I was sort of lazy. Because you can, so for, yeah, let me be very, 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 very unprecise. So for characteristic big enough, everything I said is good. Okay.
Big enough, so.
But actually, so for example, for FLN, so for type A flag variety, it's over Z, everything works. So in fact, as soon as, maybe it's fine here because we have this extra parameter. So that's a paper by Phoebe and Williamson, where they are sort of generalizing all these constructions and even to intersection cohomology. Like they leave characteristic 0 and you can just work over whatever field you want. And so, and I would say that probably it's enough, but it's not enough actually. Yes, it is. So it is, I think it should be enough that whenever you have a vertex and you look at the edges, at the edge label, then they are pairwise linearly independent over the field. And if this happens, so for example, for type A is always the case because you have always like roots, which are sort of EI minus EJ, then everything should go through. So you can compute not only cohomology with rational coefficient, but with coefficients over whatever field has this property. And it doesn't matter, I mean, it doesn't have to be algebraically closed. This only really depends on the characteristic. Yeah. So of the base field. Yeah. Yeah, but being over that, that's another story. Yeah. Yeah. And maybe I should also mention that actually if you have something which is smooth, then whatever we said is actually true. So the GKN theory is true for any generalized cohomology theory. So it doesn't have to be equivariant cohomology. You can have whatever theory you like. So,
Thank you.
Any other questions? Okay, so Evgeny had one other question.
I wanted to ask about the multiplication structure. Do you have some formula for the multiplication of those Schubert cycles?
Not yet. No, that's somehow, that was somehow it was really the point of starting whole the story. Because somehow if you only cared about the group structure, then you could just play with cis directions. While the main point is that you have a ring and you want to play with that. So, so the nice thing is that, as I was mentioning, you can find a nice basis. That is what you call the generalized Schubert, whatever class. And this has sort of triangularity property, so you can control something. So in the sense that, so you can, whenever you multiply two elements, then you know where, so you expand it again in terms of the basis. You know where the support is going to be. This is something you can control by the way the basis is defined. We, well, we don't have formulas yet again, but somehow for Schubert classes. So what you do is actually, well, what you do, it depends. So you have, you really would like to have this Littlewood-Richardson, equivariant Littlewood-Richardson rule, which is in general hard. So you don't really have it even for general flag varieties, right? So you, like to have a closed formula, it's pretty hard. So I think what one can hope at least is to maybe get a formula for the classes, which is already something, and then in the specific cases you can try to multiply that. It is still, I mean, having this triangularity properties is pretty nice. So it allows you to prove several results, like for Schubert classes.
So thank you, Martina. So now we have a break of 1 second. I have to see what the time is. Okay, so we have a break of about 45 minutes, and we'll return at 1 p.m. Eastern time.